In this video, we're going to be talking about manipulations of K. We introduced Kp and Kc last time. We know how to compare Q and K. This doesn't necessarily focus on Q much at all, this video. It's mostly just focusing on details associated with K for different reactions, and again, how you can relate those two. The first thing we're going to talk about is Kp versus Kc. So remember, the idea with Kp and Kc is that Kc is the K that you're going to use when you have concentration units given and you want concentrations in the end. Kp is going to be the K that you use if you want pressure units to be in your manipulations and you want pressure units at the end. Okay, we're going to assume that this Kp is going to give us, for our answers, units of atmospheres, and Kc is going to give us units of molarity. All right. Well, these two relate to each other. So for a given reaction, if there's gases involved, like this sample reaction here, where we have reactants A and B and products C and D with stoichiometric coefficients small a and small b and stoichiometric coefficients small c and small d, all right? This has a Kp and it also has a Kc. So we'll see some examples where we want to do a problem and come up with a molarity for our answer. Well, then we'll need Kc. But if we want to do a problem with all these gases and we want an answer to have atmospheres as the unit, then we need to know Kp. So the relationship between Kp and Kc is shown right here. So what you do to go back and forth between the two, and again, it depends on the answer that you want in terms of the units, is Kp is Kc times the quantity RT to the delta N as a power. This is our gas R here, all right? So R is 0.08206 liter atmospheres per mole Kelvin, but remember, for these Ks, we don't really care about units. It's there, but we don't really worry about it. We just know what the units of our answers are going to be. And then T is temperature, but it's in Kelvin is what you have to remember there, okay? So this is the way to go between Kp and Kc. Now, delta N is the superscript there, so it's the exponent. So what does delta N equal? Well, what you do is you take all your product stoichiometric coefficients and you add them up. Now, for this simple example, there's only two products. So we take the stoichiometric coefficient C and the stoichiometric coefficient D, and we add them together, all right? Oh, and then what we do is we do the same sum for the reactants, which for this case will be A and B. And then what you do is you subtract those two sums. So for this simple example, it would be C plus D minus the sum of A plus B. That's your delta N. All right. Now we're going to do an example where we sort of prove this. But again, just details associated with this. You're only ever going to use the gaseous species to throw in to this delta N equation. So if there was a solid or a liquid here, we wouldn't really worry about it. And we talked about that before. Okay. So literally what you do is, and if there was only like one product, so say there was only this C, then there would only be that C there. So you just take all the stoichiometric coefficients of all your gaseous products, sum them up, all the stoichiometric coefficients for your gaseous reactants, sum them up, and then subtract the two, and that's your delta N. So this is kind of a confusing formula until you kind of see it in practice. So let's take a look at an example. And let's look at a reaction and let's calculate both Kp and Kc for this reaction. So let's take a look at 2H2 gas plus O2 gas in equilibrium, right, with 2H2O gas, all right? So we know how to write our K expressions for each of these situations. So let's say we wanted answers in atmospheres. We would have a Kp that looks like, all right, ooh, let's make this, just to drive points home here. Let's make this liquid, all right. So 2H2 gas plus O2 gas gives me 2H2O liquid. Well, remember what we do with this liquid, all right? In our K expression, whether it's Kp or Kc, liquids don't have concentrations. We replace that with a 1. I just wanted to make that change to review that idea. Now over here, these two could have a concentration. They have pressures in this case because we're looking at Kp. So I'm going to write this as the pressure of H2, stoichiometric coefficient, means I'm going to square this, times the pressure of O2 raised to the first power. That's what Kp looks like. Now to go between Kp and Kc, right, what we're essentially going to do now is we're going to prove this expression right here. All right. Okay. What we're going to do to prove this is we're going to remember the ideal gas law that says that P is equal to N, and I'm going to write this like this, RT over V. And remember, whenever you see an N over V, that's moles per liter. So P is equal to concentration times RT, right? And I know we talked about this in class before, but remember, this is how you go between pressures and concentrations. And so then you can kind of see where this is coming from now, right? So what we're going to do is we're going to try to build Kc here by putting this in to each spot there, okay? So this expression becomes, right, 1 on the top, right? This is still Kp. Now pressure of H2 squared, well, pressure of H2 means I can write this as concentration of H2, all right, times RT. That whole entire pressure needs to be squared, so this thing needs to be squared, right? Here, this is the pressure of O2, so I'm going to write this as the concentration of O2 times RT, all in the bottom, right? This would be raised to the first power. That's implied by not putting anything there. So if you look at this, okay, let's just gather up our concentrations and gather up our RTs. So what we have here is Kp equals 1 over concentration of H2 squared concentration of O2 raised to the first power. There's 1, 2, 3 RTs in the denominator, all right? So it looks like there's an RT cubed down here once we combine up the RTs, right? Now, if I gave you this from the start and I asked you to write Kc, okay? Let's just see. That's something else you should be able to do. If you were going to write Kc, you would write it as K. C is 1 over concentration of H2 squared, concentration of O2 raised to the first power. And if you look at what we have down here, right, that right there is Kc, right? That right there is Kc. So I'm going to rewrite this Kp based off of that identity that we just found. And this is going to be equal to Kc. Remember we had RT cubed, but it was in the denominator. I'm going to write it as RT to the minus 3. Now, if you remember the expression that we're trying to go for, right? Remember that it's always Kc times RT to some number up here. Well, let's look at delta N here. So if I'm going to try to calculate delta N for this situation, delta N would be equal to, oh, I don't include this at all. So why do I not include this in my delta N? I'm going to say there's actually 0 stoichiometric coefficients on my product side. And why is that? Remember, we only care about gases, right, for this type of analysis between Kp and Kc. So I see there's this liquid here. That means there's 0 gaseous stoichiometric coefficients on that side. How many gaseous stoichiometric coefficients do I see here? I see 2 and a 1. 2 plus 1 gives me 3. Oh, my delta N is minus 3. And that's what I see in this expression. So the general expression that we had earlier, we see now how it works in the context of this example. I just want to emphasize this one more time. So why are there 2 different Ks for this reaction? If we wanted concentration information, all right, we would use Kc because there's concentrations inside here, and then calculations involving that value will give me concentration units for my answer. If I want pressure units for my answer, then I'll use Kp. Pressure information will go in and pressure information will come out. And on the next video, we'll actually start to do calculations involving Kp and Kc and actually solving for pressures and concentrations. And then, you know, paying attention to units definitely becomes important. So we're going to finish this video then talking about other things that you can see for any K. So everything that we talk about from here on in, it applies to any K that we run into, KP or KC. We're going to run into different Ks throughout the semester. You can always do this to for any K. So we're going to call this manipulations of K. And I'm not even going to give it a subscript because, like I said, it applies for any of the Ks that we're going to talk about. All right. So we're going to introduce some rules and then we're going to prove them, okay? So rule number 1 that we're going to introduce here is that if you flip a reaction, all right, you're going to get a new K because the products and the reactants, they actually kind of switch positions. And the new K is 1 over the old K. All right, so K new is 1 over K old, okay? When you have an equilibrium, right? This is right 2B. Let's write a simple equilibrium where A gas is going to 2B gas, right? And A and B are just stand-ins for any sort of molecule we might have. When you write an equilibrium and you're giving it the opportunity to go forward and reverse, what you define as reactants and products is kind of arbitrary, all right? So sometimes it might be useful or helpful or make more sense to flip a reaction. If I look at this reaction right here and I write its, let's just say Kp for instance, Kp here is going to be pressure of B squared over the pressure of A. Well, what happens if I instead decide to analyze a reaction that looks like 2B gas going to A gas, right? Well, if I look and write that Kp, and this will be like our Kp new, this Kp, okay, so there's my pressure, my product. Here's my pressure, my reactant squared. Oh, wait a second. How did I go from here to here? These two reactions look like we just flipped the reaction. And we'll see that we'll have to do this eventually where it'll be just really helpful for us to flip a reaction to define A as a product instead of a reactant. It's not something that's necessary for certain problems, but for certain problems it is. So what did I do? I flipped this reaction. Well, what happened to Kp? This is like my new Kp here, right? And this is my old Kp. How do these guys compare to each other? Well, it really just proves this relationship up here. My new Kp, Pa over Pb squared, it looks like 1 over my old Kp. And just to remember how that could work, right? Let's say I flip my reaction. Kp looks like 1 over Pb squared over Pa. And whenever we have a fraction in the denominator, how do we sort of deal with that? We invert and multiply. And what are you left with? All right. So essentially all this does down here is prove this thing that you need to know. When you flip a reaction, you actually get a new K, and new K is 1 over the old K. The other things we'll do with Ks is at times we'll multiply by a coefficient. And when you multiply by a coefficient, and that could be division as well. Remember, division is like multiplying by the inverse. So when we multiply by any sort of coefficient, even if it's a fractional coefficient, so you have a reaction, you want to actually change the stoichiometry, keep it consistent across the way. When you multiply by a coefficient, all right, your new K that you get, because the stoichiometric coefficients change, so the actual K expression will change, looks like your old value for K raised to whatever that coefficient is. So this number here is going to be that coefficient that we're talking about. So when you multiply a reaction by a coefficient, you take your old K and you raise it to that power. So K new is that old K raised to that power. So a quick little rundown. So let's say we had a real simple situation. A aqueous going to B aqueous, okay? So if I write my K for this, and it's going to be a Kc, I'm going to have concentration of B on the top, concentration of A on the bottom, both raised to the first power. So this is like my old K. So what happens here if I put, oh, well, really in my manipulations, or really there's some physical reason that I want to sort of write this as 2A, and 2b. Well, here's my old one. I multiplied by a coefficient. So what happens to my k now? Well, what I'm going to do is I'm going to take what my old k was, which was this inside here, whatever this number is that you multiply by, it now becomes, right, an exponent. And this makes sense if you look at it, because if you were going to look at 2a and 2b, how would you write this kc expression? You would write it as, oh yeah, concentration of b squared over concentration of a squared. And what do you get from this manipulation here? You get the same thing. So it's a quick and fast little rule. When you multiply by a coefficient, it becomes, right, that exponent in the k expression, okay? So one more time just to review here. This expression would have this k, but as soon as I put stoichiometric coefficients there, then those get raised as a power of the old k to become the new k. So this is our new k here, and this is our old k here. And like I said, that's the same as if I multiply by 1/2 here, right? That's like dividing by 2. Then this becomes b to the 1/2 and a to the 1/2. Whatever these are here, they have to mesh up here, right? And the last manipulation of k that we have to talk about is we can add reactions together to get an overall k, all right? And when you do that, right? So if we add reactions together, kind of think of like a Hess's law type problem. When we add reactions together, right, the new k is a product of the individual k's for the reactions being added. So when you add reactions together, the new k that you get for your total reaction is a product of the individual k's for the reactions being added, right? So it's a product. So when I say it's like Hess's law, it's like we're kind of building reactions from other reactions, but how it's different than Hess's law is you have to remember to multiply the things together. So let's take a look at an example. Let's say we had 2a gas plus b gas yields c gas. And down here, let's have b gas yields 3a gas. Right. Let's say that this is K1. Let's just call it K1, and this has a K2. So this has an equilibrium constant. We're going to call K1. This has an equilibrium constant that we're going to call K2. If I add these together and use my rule, notice there's 2a here, there's 3a here. These guys are going to cancel each other out, and what we'll be left with is a single a on this side. This C gas is going to be brought down as a product. These B's will add together. We'll get 2B gas. So if I add these guys together, I get 2B gas gives me A gas plus C gas, all right? This K down here for this reaction that we're going to call K3, this new reaction that we get as we add these guys together, this looks like K1 times K2, okay? So that's the application of the rule. Now we're going to prove it just real quickly. If you look at what K1 looks like, right? Well, let's write K3 first. If I look at this overall reaction right here, right? I'm going to write this Kc, for instance, as concentration of A to the first power, concentration of C to the first power, concentration of B to the second power, right? Because of the stoichiometric coefficients, right? What this tells me is this should be equal to K1 times K2. So let's go ahead and write those and multiply and make sure that this is equal. And like I said, this is a proof, right? Can I just take this and multiply to get this? Well, K1 is going to look like C over B A squared. K2 is going to look like, A to the third, before we canceled, that was a 3 there, over B, right? And if you look at what happens here, The c comes here. Oh, yep, matches up there. There's two b's here. Yep, that's a b squared. How would I simplify this mathematically? These two would go away, and you'd be left with a 1 there. All right, so this proves the point. When we add reactions together to get an overall reaction, the new K that you get out for your overall reaction, it's a product of the individual Ks. So from here we go on to solve problems involving K, but we need to know that these manipulations exist. All right, so please practice these, and as always, if you have any questions, make sure you send them off to me.